Hi, welcome to the channel. Today we are going to discuss about common emitter characteristic of a transistor. When we are considering common emitter characteristic of transistor, I am going to make the characteristic graph of NPN transistor. NPN transistor. Now, as the name common emitter, emitter will be common in this transistor. This is our emitter terminal, collector terminal, and this is our base terminal. Transistor is NPN, so it is represented by the arrow from base to emitter. Now we need to connect emitter, that will be millimeter, and also we need to measure the voltage across this terminal. So we will connect a voltmeter across the terminal of emitter and collector, that will measure the VCE, and we will supply the potential difference across this terminal using a variable source. This is NPN transistor, NPN, and collector base junctions should be reverse bias, so that's why N side will be connected with the higher potential of the battery. This is a fixed supply source VCC. Now emitter is connected with the ground, and we are going to connect base with the emitter using suitable energy source. This is a variable resistance. This is P side, this is N side, and base emitter junction should be forward bias, so that's why it will be connected with positive and this will be connected with the negative. We need a voltmeter which will measure the VBE, base emitter voltage, and also we need a emitter which will measure base current. R1, R2 both are variable resistance. VBB fixed DC source. This is connected with the positive side of the battery. This is positive side, this is negative. This is positive, this is negative. So positive terminal of voltmeter is connected with this and negative with this, and also this is positive terminal of the voltmeter, this is negative terminal. Here emitter connected to the base will be micro emitter. Because the base current is too low, so we will connect a micro emitter, and its positive terminal is connected with the positive of the battery and negative in this manner, and same here, this is connected with the positive, so that's why it is the positive terminal of emitter, and this is negative terminal of emitter. Now we are going to discuss about input characteristic of common emitter. Input characteristics of common emitter configuration. In case of input characteristic, we will plot the graph. We will plot the graph between input current that is IB and input potential VBE at constant output potential VCE. That means the graph plotted between base current and base emitter voltage at constant collector emitter voltage is known as input characteristic for common emitter transistor. So, we will take vertical axis as input current, this is our IB and this is VBE. Now, IB is in microampere and this VBE is in volt. See here, we have connected two back-to-back PN junction diode. This is forward bias and here we have supplied reverse bias. You can say negative terminal, negative potential and here positive. This is plus sign is only indicating the forward biasing and minus is representing only reverse bias. Now, when VCC which is being controlled with the resistance R2, rheostat R2, VCE is 0. When VCE is 0 and we are supplying potential to this base to emitter VBE, it means we are considering this. In that case, our output current will be 0. This will act as a simple diode, but this is connected to reverse bias. That means here negative potential will affect its working, so some potential will be dropped. In that case, at a particular point, current will rise sudden and before it current will be 0. Let this is our 0.6 volt and a constant collector emitter voltage is 0 volt. Again, I have increased collector emitter potential. In that case, the current will be 0 for more potential and it will suddenly rise in same as a simple diode. VCE is equal to 2 volt, that is let 0.8 volt. And similarly, as you are going to increase the collector emitter potential, in that case current IB will follow the same manner and the potential will be increasing. This is the input characteristic of common emitter transistor and this is particularly for NPN. See here, as we are increasing the potential difference, in that case current is also being increased. So there is an input resistance. So input resistance for common emitter configuration is the ratio between input current IB and input potential VBE. But this is resistance, so that's why ratio will be VBE upon IB. R input is equal to del VBE upon del IB at constant collector emitter voltage. So you can say that ratio between input potential to the ratio between input potential to the input current at constant collector emitter voltage is known as input resistance. The input resistance of common emitter circuit is much higher. Why? Del VBE is in volt and del IB is in microampere. Del VBE is in volt and del IB is in microampere, so that's why here R input is much higher, and it is the order of about 750 ohms, while in common base configuration the R input is nearly equal to 50 ohms, but in common emitter configuration the R input is higher and that is 750 ohm. So that's why input resistance in common emitter configuration is higher. For the given emitter collector voltage, the base current in the beginning increases at a slow rate. From the graph, we have concluded that for a given collector emitter voltage, the base current is increasing very slowly, and after a particular region it is increases rapidly. Second thing, the increase in emitter collector voltage begins about the very small decrease in the base current. In fact, for commonly used DC voltage, the effect of changing the VCE may be negligible. Next point is output characteristic of common emitter configuration. Output characteristic is graph between output current that is IC, and output voltage that is VCE at constant base current, that is our input current. Okay. So when we are going to plot the graph between output, then vertical axis consists collector current and horizontal axis will consist collector emitter voltage VCE, that is in volt, and IB, that is in IC in milliampere, and IB should be constant. Now when IB is kept 0, IB is equal to 0 microampere. In that case, our graph will be like this. Now here IB is 0 microampere. Now we are going to increase the IB current, then output will be increased and it will be constant after particular region. Suppose IB is equal to 10 microampere. Similarly, IB increased to 20 microampere, and again IB is increased to 40 microampere. Then we are observing that the graph is being increased. Okay. In this region we are getting no current. This is active region, this is cut off region, cut off. Here current is being increased with the increase in the potential. This is our saturation region. Okay. Up now our output, that's mean output resistance. Resistance is the ratio between potential difference and current, but here output resistance, so that's why output resistance is the ratio between output current, that is our IC, ratio between output potential VCE to the output current IC at constant base current is known as output resistance. For common emitter configuration. So our output is equal to change in VCE upon change in IC at constant base current. From this diagram, it may be noted that collector current is not zero. Collector current will not be zero at any condition. When base current is zero, it has certain value that is known as reverse leakage current. Reverse leakage current. This is our reverse leakage current. It's mean the collector current in common emitter configuration at zero input current is known as reverse leakage current. The saturation, active and cutoff region of common emitter modes are shown. This is our saturation region and this is our active region. Now, collector current, base current characteristic. That's mean we are going to discuss about input and output current. So third point is collector current, base current characteristic. Collector current, base current characteristics. We will keep collector current on vertical axis IB and this is our IC. IC is in milliampere, IB is in microampere. Now, we have observed that at zero voltage there was a certain current. In that case, the graph will start in this manner. Let this is at VCE is equal to 2 volt, then as we increasing the VCE is equal to, let this is 10 volt. We are saying that if base current is negative at a particular region, then collector current is 0. Otherwise, at 0 base current there is a certain collector current. Now, it is the graph between collector current IC and base current IB, keeping emitter collector voltage constant and the base current is varied as corresponding to the collector current is noted. Okay. Now, current gain in common emitter configuration. Current gain in common emitter configuration. As we know that what is gain? Gain is the ratio between output to the input. So, when we are considering current gain, then ratio between output current IC to the input current IB at constant collector emitter voltage. This is denoted by beta. When we are considering DC current gain, so beta DC is equal to IC upon IB at constant collector emitter voltage. Now, when we are considering AC current gain, then beta AC is equal to change in output collector current del IC upon change in input current del IB at constant collector emitter voltage. Current gain as defined as the output current to the input current at constant collector emitter voltage when we have considered the DC current gain, in that case it is the particular output current upon particular input current at constant collector emitter voltage. But when we are considering AC, in that case change in collector current to the corresponding change in input base current at constant collector emitter voltage. The current gain beta DC is in common emitter circuit is very large, as collector current is measured in milliampere and base current is measured in microampere. So that's why beta is larger than 1 always, and it is too much large because IC is in milliampere and IB is in microampere. So current gain in common emitter configuration is larger. Now we have studied about two type of current gain. One was the alpha in common base configuration and beta in common emitter configuration. So now the relation between alpha and beta, relation between alpha and beta, in that case we know that emitter current IE is equal to IC plus IB. This is for DC, and for AC change in emitter current is equal to change in collector current plus change in base current. Okay. From here, change in base current IB is equal to change in collector current, change in emitter current minus का change in collector current. We know that beta AC is equal to change in collector current upon change in base current. So that's why put the value of del IB in this equation. Beta AC is equal to del IC upon del IE minus change in collector current. Now divide this equation by IE, change in emitter current. It can be written as beta AC is equal to change in collector current upon change in emitter current divided by 1 minus change in collector current to the change in emitter current. From this calculation we can write beta AC is equal to del change in collector current to the change in emitter current. This is known as alpha. Alpha is equal to del IC upon del IE. So it will be written as alpha upon 1 minus alpha. This is relation between beta and alpha, and we are calculating beta AC, so that's why it is also beta AC and alpha AC. So, and for beta DC, similar, it will be equal to alpha DC upon 1 minus alpha DC. So commonly we can write down beta is equal to alpha 1 minus alpha. Current gain in common emitter configuration is always equal to the current gain in common base configuration upon 1 minus current gain in common base configuration, and beta is always greater than 1. Next point, relation between current relationship in common emitter configuration. Current relationship common emitter configuration. In this case, we know that IE is equal to IC plus IB, and IC is equal to alpha time of IE plus ICO. Here alpha is used for DC because we have considered no change in the current. Then it can be written as IC is equal to, put the value from this equation, we can write down alpha DC in bracket IC plus IB plus का ICO, where ICO is the current due to minority charge carrier present inside the collector. Just change the side, IC will be common, 1 minus alpha DC is equal to alpha DC into IB plus ICO. So IC is equal to alpha DC IB upon 1 minus alpha DC plus ICO upon 1 minus alpha DC. We define beta current gain, that's mean the relationship between alpha and beta. Then we have found that alpha DC upon 1 minus alpha DC is always equal to beta DC. So that's why IC is equal to beta DC IB plus ICEO, where ICEO is equal to ICO upon 1 minus alpha DC. ICEO, here we have considered the effect of emitter also, so that's why we have written down ICEO. ICEO is reverse leakage current that would flow between collector and emitter if the third terminal base were open. It may be noted that magnitude of ICEO is much larger than ICBO. ICEO is equal to ICO upon 1 minus alpha DC. Here it is also written as ICBO upon 1 minus alpha DC. The relation the relation IC is equal to beta DC IB plus ICEO connects collector current with the base current in the term of beta DC. This is a final relationship between input and output current. Thanks.